Welcome to the Chapter 5.5 lesson video. This is the second part, so 5.5b. We are going to solve more exponential equations. And we'll talk about this in class and kind of talk for strategies on recognizing when to use which methods. We've already done problems where they have a common base. Today we're going to do other problems. And so really this is just a variety of type of problems. I'm going to demonstrate a handful of problems of differing styles. So I would encourage you, write the problems down with me, maybe pause the video, try it or something like that as we go would be a good idea. In class, we'll go over these strategies and kind of flesh it out a little bit more and do some more practice. So let's go ahead and get started. All right, so we're going to be solving exponential and log equations. You're going to want to get out a calculator. If you don't have a calculator, there is a great website you can use. This website is called Desmos. That's DESMOS. It's a free graphing and scientific calculator online. On Google Classroom, I have a tutorial on how to use Desmos, and I'll go over it a little bit in class if I haven't already. All right, so tip number one, if solving an exponential equation and they have a common base, you can set the exponents equal to each other and solve. We've already done this one, so this is just a quick little rehash, but this is tip number one. If you can make them have a common base, make them have a common base. So for example, we can change this to 2 squared to the 2x, and we can change this to 2 to the third to the x minus 5, and then you multiply, so this becomes 2 to the 4x equals 2 to the 3x minus 15. Make sure you distribute that 3 right there. Now the base is the same, so the exponents are equal as well. So you get 4x equals 3x minus 15. Subtract 3 over, you get x equals minus 15. All right, there we go. So that's our first one, our first example. We've already talked about this before. So tip number one is something you should feel a little okay with already. Tip number two is if there is no common base, then you can take the log of both sides and simplify it to calculator-ready form. Once it's in calculator-ready form, you can then plug it into your calculator, get a calculation, and have an approximate answer. Now remember, your calculator will likely only do log base 10, so it is pretty important to make sure that you use log base 10 when you're taking the log of each side. So let's go ahead and see that. So what I'm going to do on this first one is I'm going to take the log of each side. Log of 7 to the x equals log 10. Now the reason I do this is because we have our rule about logs. Our rule about logs says that if there's an exponent, we can move that exponent down in front and change it to multiplication. So this will get rewritten as x times the log of 7 equals the log of 10. There we go. That helps us a little bit. We can then get the x by itself by dividing the log of 7 over. So we'll get x equals log 10 divided by log 7. And luckily, we did this in log base 10, so we can now plug this into our calculator. So we plug log 10 divided by log 7 into our calculator. You just order of operations. If your calculator struggles with that, you can go ahead and plug them in one at a time. And that is approximately 1.18. I like to go 2 decimal places if it doesn't say, just so that way I get a little bit of accuracy. And there's my answer. All right, so our second example here is fairly similar. Once again, we're just going to go ahead and take the log of each side. So we'll end up with log of 3 to the x plus 2 equals log of 11.5. Once again, we can take that exponent piece, this time it's an x plus 2, and move it down in front. So we can take the whole piece and move it down. So it becomes x plus 2 in parentheses times the log of 3 equals the log of 11.5. We can then divide the log of 3 over. We get x plus 2 equals the log of 11.5 divided by the log of 3. And then last, we got to get that x by itself, so we're going to subtract the 2 over. So we get x equals exactly log of 11.5 over log of 3 minus a 2. We can go ahead and plug this into our calculator. So we'll plug it into our calculator and get log 11.5 over log of 3, and then minus 2 from the whole thing, and you get about 0.22 as our answer. So we can go ahead and box that, and that's good to go. All right, let's keep going. All right, so tip number 3, it says if an equation equates logs with a common base, then you can just set the inside parts equal to each other, right? So just like before, when we had exponentials with a common base, if we have logs with a common base, log base 7, then we can just set the inside parts equal to each other. That's the nice thing here. We can set the inside parts equal to each other, and this is what we'll get. We would get x squared equals 4x minus 4. Now this is a quadratic, so we're gonna move everything to one side. So we get x squared minus 4x plus 4 equals 0. We'll go ahead and try and factor that. So we'll get x minus 2 times x minus 2 equals 0, because negative 2 times negative 2 is positive 4, and negative 2 plus negative 2 is negative 4. And so we'll get the two answers, x equals 2 and x equals 2. So that's really just one answer. Now, we're going to check this answer. So one thing we have to do is we have to check our answer, because with logs, you can only take the log of a positive value. You cannot take the log of a negative value. We can talk a little bit about that more in class if anyone's curious. But when we plug our number in here, that number that we plug in has to be a positive value. So this is x equals 2, I accidentally erased it, has to be a positive value for each log. So if I put a 2 in here, 2 times 4 is 8. 8 minus 4 is positive 4, so that's still okay. Put my 2 in here, 2 squared is 4. 4 is still a positive value, so that's okay. If I put it in any of these places and that stuff that was in there made it negative, then it'd be an invalid solution, like with a lot of other problems. So since it was a valid solution, we checked it, it's good to go. We'll hopefully see another example later that has some invalid solutions. All right. If it's possible to use log laws to manipulate what's going on, then that would be a good idea. And you can then change it to exponential form. And once again, you always got to check your answers to make sure they make sense. So there's kind of two tips here. The first is if you have just a log equal to a number, so just a log equal to a number, change it to exponential form. And we'll do that in just a second for this first one. Or if you have two logs and a log law, like log base 10 plus log base 10, you can combine those together. One of our log laws allows us to combine those two together and multiply what's on the inside and have them become one log, and then do the same thing. So let's go ahead and try that. So this first one, since it's just one log equal to a number, we can change it to exponential form. So we're going to change this to be 5 squared, so 5 to the second power, the base to the second power, equals what was inside the log, which was 7x minus 2. All right, so 5 squared, that's 25, equals 7x minus 2. Add the 2 over, you get 27 equals 7x. And divide by the 7, you get x equals 27 over 7. And this is okay to leave like this. There's no log, so that's a good final answer there. This next one, we do have to do a pre-step here. We have to combine the two logs together. So we can multiply those together, and this can become log base 10 of x times 4x, okay, equal to 2, right? That's one of our log laws, that if you have two logs with the same base being added, you can combine them to one log with what was on the insides being multiplied, okay? So then we can change that into log base 10 of 4x squared equals 2. And then since it's a log base 10, we can change it into 10 squared equals the inside, which is 4x squared. Okay, so then we can change that into 100 equals 4x squared. Let me change that real quick. That shouldn't be like that. 100 equals 4x squared. Divide both sides by 4, you get 25 equals x squared. Take the square root of each side, and you get x equals plus or minus the square root of 25. And simplify it, so you get x equals positive 5, x equals negative 5. Now, We got to double check, make sure that if I were to put either of these answers back in, it doesn't make one of the insides negative. So let's look at positive 5. Positive 5, that's okay. Positive 5 times 4 is positive 20, that's okay. Negative 5, though, that would be a negative inside the log. Or negative 5, that'd be a negative 20. So that one is an invalid solution. We'll cross that one off, and our only answer is x equals positive 5 here. Okay, so let me draw a little arrow here for anyone that's looking at that. So what we were doing is we combined these two pieces together to make them into one log. We multiplied that together. We then take a log base 10 to the second power equal to 4x squared. We squared the 10 to make 100. We divided by the 4 to make 25. We took the square root, plus or minus square root of 25. Don't forget that plus or minus piece whenever you take a square root of both sides. So that gave us 5 or negative 5. 5 was okay, but negative 5 when it plugged in made at least one of the logs equal negative, so it was invalid. All right, last example, and this one's a little trickier, and so I want to show it to you. This is more of a challenge type problem that you might run into, not necessarily something that we would test you on, but it would be a challenge problem. If there is no common base, then really your only option is take the log of both sides to move those exponents down. So we're going to make this log of 3 to the x plus 2 equals log of 5 to the x minus 1. We'll move those exponents down, so it'll become x plus 2 log 3 equals x minus 1 times log 5. Now what we're going to do a little bit different here, because it's not going to quite work out the way we want. What we're going to do is we're going to distribute our log to both pieces here. Same on the other side. Distribute our log to both pieces and kind of expand it out a little bit. So we'll get x log 3 plus 2 log 3 equals x log 5 minus 1 log 5. All right, now what we're going to do is we're going to move both the pieces with an x to one side. Okay, so I'm going to move this piece over here, and all the pieces without an x to the other side. So I'm going to move this piece over here. Okay, so that'll look like this after I rewrite it. It'll look like x log 3 minus x log 5 equals negative 2 log 3 minus log 5. I'll move up here. Okay, now I'm going to pull out that common factor of an x. You'll notice when I put both these with the x on this side, now they have a common factor of an x. I'm going to pull that out. So I will get x times log 3 minus log 5 equals negative 2 log 3 minus log 5. Nothing changed over there. And then last, I'm getting the x by itself. I'm going to divide that over. So I'll get x equals negative 2 log 3 minus log 5 over log 3 minus log 5. So that's a little bit of a messy problem, a little more complicated. But the idea was we took the log of both sides, distributed things out. Everything with an x went on one side, so we moved everything with an x on one side so we could factor it out as a common factor, and then divided the other stuff back over. The last thing we should do here is plug this into our calculator. If we plug it into our calculator, we get an answer of approximately 7.45. And that's our final answer. So a little bit trickier. We got it into calculator form. We then plugged it into our calculator, and we got 7.45 as our final answer. All right, so once again, this is a bit of a challenge problem, not something you'll see on every single problem that we do, but it is something that might be a challenge problem that gets thrown your way. So with that, if you have any questions, please don't hesitate to reach out. Otherwise, I'll see you guys in our next live session, and until then, I hope you have a great day.